line, which minimizes the square distance between the points in the line. That's what it does. Well, that's from a sample of 1,000. We're trying to figure out from this sample of 1,000 the actual effect for, if it's data for one city, then we're trying to figure out the actual effect for one city. If it's data for the whole country, we're trying to figure out the actual relationship between education and income for the whole country. Well, this is from one sample. Just like there's error around a poll number, 47% plus or minus 3. There's error around that slope based on my sample size. The larger the sample size is, the better guess I have at this line being closer to the true effect. But, so when I say sort of this is my line, this is the line for my sample, if I could somehow magically know the true effect between education and income in the country, it might actually be that. It might actually be that. It might actually be that. And the question I ask essentially, or the question that gets asked then, of whether I'm certain that there is an effect, it boils down to a hypothesis test, a null hypothesis, which is that the slope is equal to 0, and an alternative hypothesis that the slope is not equal to 0. And you can calculate a p-value about this, and then you have a confidence level. But the basic sort of gist of a significance test with regression is the answer to the question, does education actually affect income, is the same as asking the question, is the slope actually different from 0, or is the slope not different from 0? Can I say for sure that the slope is different from 0? If it's so uncertain that the possible slopes actually cross over 0, like that, where it's not positive, then I fail to be 95% confident that there's a difference. Let's leave that up, and let's actually look at an example. And go through these three things. And before I get to the computer stuff, I gave you 3 regressions here. Let's go to the bottom one first. There's 3, or the summary output on the bottom one. And I should have brought it. And let me just sort of draw up this. Popularity here, and house seats lost here. And you've got popularity, 30%, 40%, 50%, 60%, 70%, pretty much all the data fits in there. And then house seats lost, 10, 20, 30, 40, 50, 60, 70. And then you've got data points out there. And actually, when we're doing the data points, actually look like this. With a regression line that looks something like that. Why do I say house seats lost? Because every year since 1948 except one, with one exception, which is 2002, the party in power lost seats in the House. So, the norm, the complete norm, is, and the win was basically sort of just about even in 2002. It was a slight gain or push. But so, in this case, the relationship actually will take a negative slope, because as the president gets more popular, what do? They do better. When the presidents get less popular, they do worse. My hypothesis, my null hypothesis, is that the slope is just going to end up being equal to 0. My alternative is that the slope is actually, for sure, not equal to 0. Or that popularity has an effect. So go to the third one now. If you go to the regression, the first thing to look up is up in the top. The second term down is r squared. Notice it says r squared. Multiple r is just the correlate. You ever heard of correlation? Correlation coefficients? Well, that's r. So you square that. And so you get r squared. So you might know that if you square that first number, you get the second number. But r squared, which is the second one there, is the percent of the variation in y that's explained by x. Or in our case, 55.7% of the variation in house seats lost can be explained by a linear relationship to the president's popularity. 55%. That means that 45% is unexplained. So on average then, for like the average point there, compared to y bar, for the average point there, about 55% would be explained by the line, and 45% would remain unexplained. Some years are better explained than others by the model. But so 55% of the variation is explained by a linear relationship to popularity of the president. The next term down is adjusted r squared. We'll get to later. It's actually a little bit better to adjust for degrees of freedom. And we have a small sample size here, so we have a small degrees of freedom, so it's a little bit smaller. But let's not worry about that now. It's the same basic idea as r squared. It's just adjusted for what's called degrees of freedom. And if you go to the next thing called analysis of variance, or ANOVA there, in observations, there were 16 observations. That only happens every 4 years, basically. That's why I only have 16 observations since World War II. The next one then, see this term regression and residual and the total? That's what I was drawing up here. The 6009 is the total variation from y bar for all the points, all 16 points. The 6009 number there, see it? 6009? This is 1 point's total variation from y bar up to y. The total variation of all 16 points to y bar, to the average of y, is 6009. That's the total variation. The part that's explained by something called the first term, the regressor, 3,347, that's the explained. The next term, one down, the residual, that's the unexplained.